minimum value will be by just dropping a perpendicular. As simple as that. This is magic. You hardly did any calculation. We have a river of width B flowing at VR. Boat has to reach a point B from point A on one bank to point B on the other bank. This B is a distance A away along the banks. Let's go about doing this in a slightly unusual manner. We know the line AB, right? This is the line of travel, that's B. Now, instead of measuring the angle with the banks, let's use the line AB as our reference, set up x-axis along this line and y perpendicular to it. This is a little unusual, but you will see the reason why. Let the angle made by the line AB with the banks be alpha, and let the velocity of the boat VB make an angle beta with the line AB. So our x-axis along the line AB, so the equation for that will be VB cos beta plus VR cos alpha, VB cos beta plus VR cos alpha into T equals length of AB, that will be root of A squared plus B squared. And since there is no motion perpendicular to AB, the displacement along the line along the y-axis is 0. So VB sine beta minus VR sine alpha into T equals 0. This is the advantage of our choice of y-axis at right angles to line AB. Displacement is 0. When the right hand side of an equation becomes equal to 0, things become simpler, right? Solving becomes simpler. Let's see what this VB is. VR sine alpha by sine beta. Alpha is given, right? Strike alpha is this angle. Sine alpha is B by root of A squared plus B squared. So VB and beta depend on each other this way. For minimum of VB, beta must be 90. So that's it. Minimum VB is when beta is 90, that will be VR sine alpha. Sine alpha is what? B by root of A squared plus B squared. A neat solution of the problem, and well, choice of x and x a little unusually in the sense normally x-axis chosen parallel to the banks and y-axis at right angles. Here this is possible because line AB is known. If B is unknown, then you cannot choose any unknown line as your x-axis. Here B is given, so we know, well, we can choose line AB as our x-axis. We'll do this problem later on with the standard choice of x and y-axis, and you will know, well, the beauty of this solution. You'll appreciate the beauty of this solution when you do that. Let's solve the problem in a different way. The vector sum of VR and VB must be along the line AB. There's a line of motion. So if this is line of motion, say this line, then VR is like this, makes an angle theta here. Theta is known to us. Tan theta is B by A. So VR could be anywhere like this because vector sum of this is, say, VB. Now VB can be oriented at any angle to VR such that the sum of VB and VR is along this line. The vector sum of VR and VB must be along this line. And the length of that VB, consider the triangle. This is the triangle rule that we are using here. Sum of VR and VB would be along this line and will be this vector. This will be VR bar plus VB bar. The minimum of VB is when VB is at right angles to this line. right? So we found the minimum value will be by just dropping a perpendicular, as simple as that. What do you see here? This is a right angle here, and this VB minimum. So sin theta is VB minimum by VR, sin theta is VB minimum by VR, and so that VB equals VR sin theta. This theta, so this is theta. Sin theta is B by root of A squared plus B squared. This is magic. You hardly did any calculation. Well, you're being vectorial, which is not what we normally do. We prefer splitting vectors into components and writing equations along the x and y, but there is an opportunity here to do this. This is rare, but if you can find such an option, well, that would be really great.
Vector VR, shown in green, has a fixed length. Vector VB, shown in orange, has a variable length. The vector sum of the two, shown in blue, must be along the line of motion. The least value of VB is when it is at right angles to this line of motion.
Let's solve the problem the routine way. The routine way would be to choose an x-axis parallel to the banks and y-axis perpendicular to it. Let VB make an angle theta with the banks, with the river velocity. So your x equation will be VB cos theta plus VR into T equals A. And VB is sin theta into T equals B. A and B are given here. VR is given. Theta is unknown to us. And we want to find VB. T is of course unknown. We want to find VB minimum. So there are three unknowns, VB, T and theta. So what we do is we'll eliminate T from this equation and we'll get VB and theta relation. That would be VB cos theta plus VR by VB sin theta equals A by B. I'm not going to go ahead and solve this, but I'll tell you the strategy. And I'll write the equations, I'll show the equations. They will be monstrous. Cross multiply, and then to find the minimum of VB, differentiate VB as a function of dVB by d theta, set it to 0, and then you will get from that the value of theta when VB is minimum, and then you can solve for minimum VB. Lot of workout. I'll show you the equations. Well, take a look at them. Well, perhaps then you would appreciate the beauty of the earlier solutions. So the equations are routine, but the solution is going to be very long. When we chose the x and y axis in a different fashion, x parallel to AB and y at right angles, well, the equation for y became simple. There was a 0 at the right hand side. There is no such, well, ease here. This is routine way of writing equations, and you're going to do a lot of solving to end with the result. Take a look at this. I'll also show you an animation when the boat actually travels the distance, crosses the river with that minimum speed. The boat's bow will be pointing at right angles to the direction of motion. That's a very unusual kind of a travel. Boat's velocity is at right angles to the line of motion. It's moving entirely sideways. That's it. Hope you enjoyed solving the problem. 3 different ways. The non-routine ones are the easier ones.
Boat has least velocity required to move between 2 points on opposite banks. The bow of the boat is at right angles to the line of motion in this case. X and Y axes are chosen parallel and perpendicular to the river. The first equation is the equation for the x-axis and the second for the y-axis. Dividing one with 2 and cross multiplying gives us equation 3. Differentiating 3 will give us 4, and we substitute dv by d theta is equal to 0 to get the next equation, which yields tan theta is minus a by b. This is the value of theta when Vb is minimum. Substituting the values of sine theta and cos theta in equation 3 and simplifying, we get the required minimum velocity.